All right, so we just finished talking about a couple different topics, energy and collisions. And we got one last thing that we're going to talk about this unit, and that's talking about work and power. So we have already talked about work quite a bit, right? We've said that that's the force times the distance. So F delta X, it's also equal to the change in energy, or how much energy is added to the system. So the last little concept we got to talk about is power. So in this video, he talks about how energy is being transformed and how there's work being done. And then he also brings up this concept of power, which is a little bit more about how fast work is being done. And that's what we're going to examine in this section. So the last section that we're going to talk about is power. And let's get right into it. So power, if work is how much energy you're getting, power is the rate at which energy is being transformed or transferred. So work is force times distance, and it's independent of the time that it takes. It's just, hey, you get it done. So when you're little side note, when your mom tells you that you're not working fast enough, let her know that what she actually means is that you don't have enough power, because work is independent of time. Power is not. She will greatly appreciate the correction from you and let you out of whatever task you're doing. Moms love being corrected about stuff like that. Also, a side note, if you get pulled over for speeding, let's say you're doing 35 in a 25, and the officer pulls you over for speeding. Well, you say, officer, my average speed is not 25. I have to go 35 because before, when I was accelerating, my average velocity was below 25, and now I have to go faster to make up for it. And they will excuse you from that ticket. But anyway, our equation for power is actually really easy. It's just the change in energy or the work divided by the time. So our unit for power is measured in watts, and it's 1 joule in 1 second. A way that you remember the unit for power is, if I think about the most powerful actor, like of at least of my generation and my parents' generation, I always think about Arnold Schwarzenegger. And if Arnold Schwarzenegger was in my physics class and we were talking about power, he didn't know that the unit, he didn't know what the unit was, he would ask me, "What is the unit for power?" And I'd say, "Yes, that is correct." So I got a quick little analogy, and this always happens at this time of the year. What happens when it snows? Well, consider there's a ton of snow in your driveway. Now, there are many different ways to get rid of that snow in your driveway. You can have your grandma come over and shovel it. You can use a snow blower or a snow thrower, or you can hire a snow plow. Now, in each of these three cases, which one is doing the most amount of work? And the answer is, they're all doing the same. She's working to clear a driveway. He's working to clear a driveway. The snowplow is working to clear a driveway. All of the works are the same. Meaning that if you weren't home and you didn't see which method was being used, it's all the same to you, right? So power, it's not how much work you do, it's how fast you do it. It's work over time. So grandma here, she's got the least amount of power, and the snow plow has the most amount of power. It takes the least amount of time to get it done. It could probably get it done in like 2 or 3 passes at most. So anyway, that's what power is and how it compares to work. So there is one other way that we can look at power. If I think about work, work is force times distance, and that leaves us with distance over time, which is velocity. So power is also force times velocity. It's the rate at which energy causes an object to move, and that's a very specific way that you guys are probably very familiar with, and that concept is horsepower. We will also take a look at horsepower. When I think about like what a horsepower is, well, that's kind of like comparing inches to centimeters. If 1 inch is 2.54 centimeters, well, 1 horsepower is 746 watts. So it's just like it's a different unit that we often use to talk about power. So I got a quick check here. 4 students run up the stairs in the time shown. Which student has the largest power output? So power, again, is work over time. And we see that students A, B, and C are all going up the same height. They're all going up that same height of 10 meters. But it matters how much work they're doing as well. So B and C, for example, they both take 8 seconds. C weighs 64 kilograms. As you can see, it's a girl. And B weighs 80 kilograms. It's a boy. And therefore, B is doing more work than C. And we'll talk about this in the lab on Tuesday, the horsepower lab, or the next lab that we're doing. Women can never win that lab because they just don't do enough work. And it's unfortunate, but it's true. All right, and then we look at A versus B. Well, they both do the same amount of work, but B does so in less time. So then the last one I got to compare is B and D. In D, he's doing twice as much work. He's going 20 meters instead of 10, but he takes more than twice the time. So in fact, B has the most amount of power. D does not. We got one last partner problem in this unit, and that's taking a look at a car or a truck going and speeding up. You're going and speeding up from 27 to 34 meters per second in 6 seconds, and the power that you're taking to do that. So I'll set it up for you, but we'll talk about it in class. Power, of course, is your work over your time. And where do I go from this? Well, your engine is giving power because it's changing the energy of the car. And what type of energy is it changing? It's changing kinetic energy. It's changing kinetic energy in some given amount of time, which is going to be the final minus the initial over the delta time. And that's how we can figure out exactly how much power your car is exerting. One little extension that we're going to look very little at. It's not covered by the AP exam, but I think it's a really interesting concept, and that's electrical power. And I have a little demonstration that I'll show you in class on this as well. So when you get your bill from We Energies, you get sent every month, and some people call it the electricity bill, some people call it the energy bill, some people call it the power bill. Which one is actually correct? What is We Energies actually giving you? And they're charging you for kilowatt hours, which is the number of kilowatts used in an hour times the hours. An interesting little concept is that the rate for kilowatt hours is 13 cents per kilowatt hour. So you can actually calculate exactly how much it will cost to run any particular thing. And if you, the demonstration I'll take a look at is going to be an LED light bulb versus a traditional incandescent, and how much more energy is being used by this traditional light bulb. So LED light bulb is actually coming down a lot in price in recent years. I've picked up packs of these for dollars, like several dollars, not much. So actually a very, very extremely efficient way that you can change over and save money on your house, because we Energies charge you for it. They charge you for energy. They say, how much energy do I have to send this house? And they charge you per kilowatt hour. So I could do an example here, but if you take a look at running a light bulb for a full month, it costs you dollars to do that. So it's always good to turn off things before you leave. That actually concludes this unit. I've already previewed the next unit. We're going to talk about momentum is next. And it's just a different way of taking a look at objects moving. And specifically with this, as I mentioned before, we're going to take a look at collisions. That's a huge part of using momentum to solve problems. So that concludes our unit on the conservation of energy.